Okay, so for starters, nearly 70% of the Earth's surface is covered with water. That's mostly ocean. So most of the Earth's surface is water. And water plays a major role in the absorption and distribution of thermal energy. So let's discuss water's role in weather and climate. Okay, so we have to get into some more specifics again and a little bit of math. So we're going to talk about a thing called specific heat capacity. And what that is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So here you go, one more equation for us. We have a couple today, but this is doable. So the specific heat capacity can be shown as a mathematical equation, and that's Q, which is the amount of heat, equals the mass in grams times the specific heat capacity and a change in temperature. So with this, we can figure out how much heat is required for different things, or how much, and so on. We'll get into that though. And of course, remember that delta T is equal to T2 minus the first T, or an initial temperature. Okay, we're still on page 9 here, pals. So just as an example, this is a chart of specific heat capacities. And if you look here, pure water, has a specific heat capacity of 4.19. Now, just that H2O in different phases, so we have steam would be 2.02, ice would be 2.00, seawater, so with salt in it, would be 3.89, and then dry air, if you will, is about 1, and moist air, so humid air, is about 1.15. Yeah, so there we go. This is just kind of an example. So one thing to notice here is pure water's got a pretty darn high specific heat capacity. So this large specific heat capacity causes changes in weather and climate. So this is significant because, again, a huge portion of the Earth's surface is covered in water, and water has a huge specific heat capacity. So what does it all mean? Well, first, let's just talk about a few more definitions here. So we're going to talk about conduction, convection, and radiation. Radiation we've talked on, but now we have 2 new words to work on. And these are mechanisms of energy transfer. Okay, what's conduction? It's when energetic molecules from the land and water collide with molecules in the air that are close to the surface. So these collisions transfer energy from the Earth's surface to the air. The temperature of this lowest level of air eventually comes close to the temperature of the land or water beneath it. So we have our water or earth or dirt or soil or whatever it happens to be that's being heated up. So it has a certain amount of heat in it, and then through conduction that energy transfers to the air above it. Okay. So then we have convection, and convection occurs as air circulates and distributes that heat that it got from the land or the water. So as the lowest layer of air warms, it expands and becomes less dense. The warmer, less dense air rises as cooler air descends and takes its place close to the ground. So that's convection. It's actually moving. These molecules are actually moving. It's not just the energy transfer, but the molecules themselves are moving. That's what we're talking about when we talk about convection. So warm air rises. Cool air is heavier, so it sinks. So air that's near the warm surface of the Earth, or the warm water of the Earth, will warm up, and because it's warm, it rises, and because it's rising, that cold air that it's rising into will actually drop, and it'll then become close to the ground, which will then heat up because it's close to the ground. Okay, so still on page 9 here, let's review radiation. So the components of air are very inefficient at absorbing the medium wavelength solar radiation like visible light. So don't get too deep into that yet, but essentially what we're saying is air isn't very good at absorbing that visible light that we see. However, water vapor, carbon dioxide, and other greenhouse gases absorb the longer wavelength or infrared radiation emitted by the Earth. So this absorption of long wave radiation from the Earth is a major source of heat for the air close to the surface. Let's get a little visual here. So when we're talking about conduction, convection, and radiation transfers of energy, we're seeing that the sun is coming down and it's being absorbed by the Earth. So the solar radiation is being absorbed by the Earth. Some is reflected, of course, back out into nowhere. And some is absorbed by the water, vapor, and gases and stuff in the air and the atmosphere, right? Some of that solar radiation is reflected off clouds and it just bounces back into space. So the this radiation that's coming in is not really affected by the air. It just shoots right through it, not so much anyways, and absorbed by the Earth. And then that radiation, the heat that's radiating off the Earth, that's long wave. And it actually, as it's trying to escape, it's actually absorbed by clouds, water vapor, and gases. So that's what we're trying to say here. That's all we're trying to say here. Boom. So let's talk about phase changes. Let's just shift gears for 1 sec. So specific heat capacity is the energy needed to cause water and other substances to increase and decrease their temperature. So also, when a substance cools, it releases the same amount of energy that it took in. So that's just something to think about as we get into it, as we play with that equation. So one interesting thing is that water can actually absorb and release energy without changing temperature, and that's where phase changes come in. So the same amount of energy is released when water vapor condenses into a liquid or when the liquid freezes to a solid. The same amount of energy is released when water vapor condenses into a liquid or when the liquid freezes to a solid. So when these changes occur, the temperature doesn't actually change. Ice, for example, at 0 degrees Celsius changes to water at 0 degrees Celsius, but it takes energy to do that. So it's still 0 degrees Celsius, but it sucked up some energy in order to do it. So that energy is used to break the bonds between between the water molecules in the ice. So then the opposite being when water freezes, it releases energy. We're on page 10 now, by the way. Okay, so the amount of energy that's released when a mole of a substance freezes is the same as the amount required to melt it. I've kind of said this in like 3 different ways now, but that's all we're saying. Like energy in equals energy out. When we're doing a phase change, whether it like the amount of energy involved in freezing it is the same as the amount of energy involved in melting it. So similarly, the amount of energy that's released when a substance condenses from a gas to a liquid is the same as the amount that was required to convert the liquid to a gas. Okay, so let's talk equations for a sec here. The big picture here, we're saying energy in equals energy out sort of thing. If it took a certain amount of energy, or if something released a certain amount of energy when it froze, it will need that same amount of energy to melt. That's what we're saying. That's what all these fancy words are saying right here. So let's talk about that for a second. And remember, the significance of this is that there's a huge amount of water in the world, and that if water can absorb energy from the sun without changing temperature, that will have a big effect on the temperature of the Earth. Okay, moving along. So the energy required for melting is, we use this equation here where Q equals the amount of heat in kilojoules, N equals the number of moles, and H with the little FUS or fusion is the heat of fusion on the bottom there. And that's a number that we'll get, and we can manipulate this to figure things out as well. Again, don't worry if you're just like, what is this? That's okay. When we do a couple practice questions, you'll be just fine. Just this equation is in your notes, and you'll be able to use it. Okay, moving along. Okay, the opposite being true. Energy required for converting from liquid to gas would be Q, the amount of heat again, and N being the number of moles, and HVAP equals the heat of vaporization. This is on booklet page 10, and just remember, there's no reason that you would fully understand this equation right now. You haven't used it, but when you have used it a couple times, it'll be pretty direct and pretty easy and pretty straightforward. Okay. So examples of heat of fusion and vaporization, something like water, the heat of fusion is 6.01, and the heat of vaporization is 40.65. So I'm not going to just read all of these, but we can see that between substances the heat of fusion varies pretty greatly, and varies even more with the heat of vaporization. Okay, this is in your notes. You don't need to memorize this or anything like that, but these are known numbers. Scientists have figured these out for us. Okay, so now we're going to talk about from solid to a gas. And now water and other substances have the ability to be converted directly from a solid to a gas to skip that liquid phase, and that's called sublimation. That's a new word, highlight it, sublimation. When water freezes into ice, okay, so water is significant. What we're talking about is this magical thing called water. And when water freezes into ice, snow, or hail, it releases energy. When ice, snow, and hail melt, they absorb energy. How does this relate to climate? Oh, I'm going to tell you. Don't worry, pals. So we're talking about energy here, right? Energy. A huge amount of energy because there's a huge amount of water on the earth. Okay. So oceans, lakes, and rivers have a low albedo and absorb about 93% of the incoming solar radiation. So again, albedo is that ability to reflect things. And what we're saying here is that water doesn't reflect very much light, much of that solar radiation. Okay, specifically, it doesn't reflect that much of the solar radiation coming in. I know that when we're out on a boat or something, or at the beach, sometimes it seems like we get an extra sunburn because the water reflects, or because some of that, because of reflection off the water, but the water actually absorbs quite a bit of that energy, okay, of that radiation. So since water has a high specific heat capacity, paired with this low albedo, it doesn't change temperature much as it absorbs the energy. Okay, so it's absorbing a ton of energy, but it's not actually changing much temperature while it's doing it. And since water has a high heat of vaporization, it doesn't evaporate all that quickly either. Since it has a high heat of fusion, it's got to lose a ton of energy in order to break bonds with neighboring molecules or melt. So once it's ice, it also takes a lot of energy for it to actually melt. Okay, let's get a little visual here. So right here we have, we just kind of have these three phases, right? We have water vapor, water liquid, and then solid ice on our leftmost diagram here. And this visual is just trying to tell us that when water vapor or a gas becomes a liquid, heat is released. Or when water evaporates and becomes water vapor, heat is absorbed, okay? And then what are we saying here? On the bottom, we have with ice and water, same deal, right? So we're just talking about who's releasing energy and who's absorbing energy, okay? And because of these principles, there's a huge effect on the earth, right? Huge amount of water, high specific heat capacity, high melting point, or sorry, low melting point, etc. So it really can have a big influence on the climate, is essentially the big picture here. That's what we're talking about. Water is super important. Now, take a quick look over here, just those different names. We have vaporization, when it goes from gas to liquid, or condensation, when gas becomes a liquid. When something melts or goes from a solid to a liquid, it's called fusion, that's the fancy word. Or when liquid becomes a solid, that's called freezing. Now, sublimation is when a solid goes directly into a gas. And then, deposition is the reverse of that. Okay, so moving along here, let's just take one quick little look at the hydrologic cycle, or the water cycle. So here, this picture is just showing us like water evaporates, goes into the clouds, is transported over land, dumps onto the land, and then through the water table or through streams or whatever it happens to be, it manages